organizers of this very great workshop. I'm very happy to have been invited. Many thanks for them. So yeah, we'll discuss in this work about some biases, and there is one bias which is very well known among social psychologists, which is the positive bias on self-opinions. And this bias comes from a process which is natural in everybody, which is the tendency to accept positive feedbacks. When you have positive evaluations, you're happy and you're happy to welcome them. Whereas if you have negative evaluation, negative feedbacks, you tend to avoid them and to dismiss or neglect them. And as a result, you tend to over-evaluate yourself and to be optimistic about your abilities and about the possibilities of achievements that you have. This is very well documented in the social psychology literature. But recently, we have developed a model, opinion dynamics model, in which there seems to be another bias, another positive bias on self-opinions, which doesn't come from self-enhancement. It doesn't come from this process to accept positive feedbacks and to dismiss negative feedbacks. And this model suggests also the existence of a negative bias on the opinion about others. And these biases have not been detected by social scientists yet. So the main point of this presentation will be we'll build on this first model and these first results, and we'll add a new analysis of the dynamics of this model, in which we show that these biases hit differently the agents according to their status when the agents are unequal. And this process is at the detriment of low status agents, and it's beneficial to high status agents. And also we'll show a first step of an experimental work which confirms the existence of this specific positive bias on self-opinion. So this new bias that has not been detected by social scientists seems to be confirmed by this experiment. Okay, so let's start with a presentation of the model. So in this model, we have the state of the model is when you have a list of agents, each agent has an opinion about itself and about all the other agents. So the state of the model is a matrix, as you can see it here, where you have the self-opinions on the diagonal here, and the opinions of the agent 1, for instance, are on the line, and the opinion about agent 2 here are on the column 2 here. And the dynamics is very simple. We choose at random 2 agents here, agent 2 and agent 1, and these agents influence each other on their self-opinions and the opinion they have about the other. Since it could be, we could have chosen agent 2 and agent 4, and then the agent would have an exchange about the self-opinion of agent 2 and the opinion of agent 2 about agent 4, and vice versa. So what is the influence? How does it work? Well, it can be named as a noisy attraction. What does it mean? Let's say that I interact with you and you influence my self-opinion. So my self-opinion will be modified by this expression here, which is the difference between your opinion about me and my self-opinion plus a noise, which is here a uniform noise between 2 values. And this noise stands for the fact that I don't have a direct access to your opinion. So I may make mistake about what you think of me, either because you don't express it explicitly, or maybe I don't understand what you're telling me. also, we have this expression here, this modification of my self-opinion will be multiplied by the influence I give you. And this influence will be high if I have a very high opinion of you, and which is much higher than my self-opinion, then this value will be negative, and the influence I give you will be high, will be close to 1. On the contrary, if the opinion I have about you is low, and it's much lower than my self-opinion, then this value here will be positive, and I will give you a low influence. So the impact of your opinions will be low on me. So let's run this model. And we had a surprise when we ran it for a long time, starting here with 40 agents. And we start with all opinions equal to 0. Every agent has the same opinion about all the others, and this is neutral. And because of the noise, we have many changes in opinions. We see that in columns, the opinions tend to be similar. But what we get here, the color code is that for red boxes, the opinion is positive, and for blue boxes, the opinion is negative. So after a while, we have mostly the opinions which are positive, and we can see it on this graph. This graph, you have time as x-axis, and on the y-axis you have reputations, which are the average of columns. So this is the average opinion about each agent. And you see that you have most of these reputations that grow over time. And this is confirmed by this red curve, which is the average of all opinions, which grows and then stabilizes to a value which is close to 0.5. And this is surprising because the noise is symmetric and not non-biased. So there is another source of bias that we'll discuss later. But before that, there is another version of the dynamics in which, in addition to the discussion about my self-opinion and my opinion about you, we also discuss when we interact, we also discuss about someone else taken at random. For instance, here it would be agent 4. And we have the same dynamics, the same noisy attraction on all the opinions, and in both ways. And when we add this dynamics of gossip, we have a very different result, actually almost the opposite. After a while, we see it's not exactly the opposite, but we have an average value of the opinion, which is the red curve here, which tends to be negative with strong fluctuations, but on average it's negative. And we have larger dispersion of the reputations with a higher density for low values of reputation. So the reputation on average tend to be negative, and the opinions tend to be negative. And this is something you can check here on the matrix, in which you have more columns that are blue or light blue. Okay, so I won't go too much into the details to explain this. From the previous work, we had the first analysis, a first explanation, which is related to this new bias that I was mentioning in the introduction. So this bias without self-enhancement, and I will give you an idea on a simplified case of how this bias emerges. So in this simplified case, we assume again that I'm discussing with you, and in the first interaction, my interpretation of your opinion about me is my own opinion of myself, my self-opinion, plus delta. In this case, my next opinion after our interaction will be this value here, my previous opinion plus delta multiplied by the inference I give you at this moment. Now, let's assume that at the second step, the opinion I think you have of me is again my current opinion, but now minus delta. then my opinion at step 3 here will be diminished of delta multiplied by the influence I give you at time 2, but this influence will be smaller because my self-opinion is higher, and when my self-opinion is higher, I give you less influence. So at the beginning, your influence is high, and since my self-opinion increased, the influence I give you is lower, and when I receive minus delta here, my opinion will decrease less than it increased before. And as a result, the difference between my opinion at time 3, my self-opinion at time 3, and my self-opinion at time 1 will be positive here. And this is what we call this positive bias. This is the tendency of my self-opinion to increase when I have random interactions with you. Of course, here we will simplify it a lot because I have only one person I interact with, and we have this noise, which is much simpler than the noise that we have in the model, but it works similarly. And also, we can check that if we start with the negative minus delta and then plus delta, we have exactly the same result, or almost the same result. But also, and more importantly, we have the opposite result considering the opinion about others. I won't go too much into the details, but simply the phenomenon is exactly the same, except that in this case, the influence is growing with the opinion I have about the others. So we have our first analysis of the patterns that we got was that there is kind of competition between this bias on self-opinion and positive bias on self-opinions and negative bias on the opinion about others. But we couldn't go much further than this, and we wanted to have more precise understanding of this competition between the two biases. And this is what we've done by using moment approximation on the model. So the principle is that we change the variables, and the main idea, so the new variables are the change from time 0. The equation remain the same. Here we recognize the noise, and here the influence function. But the main point is that we develop the influence function around its average. So here, using the derivative of the influence function. Here we assume that this quantity is small. And doing that, of course, I don't go too much into the details, but we managed to have equations of the average value of self-opinions in the model, in which we have this quantity here in red, which in general is positive because here we have a square, and the derivative of the influence function is assumed to be negative. So since we have negative sign here, we have a positive value. Note that for the equation of the self-opinion, we have a sum here, whereas for the equation of the opinion about others, we have here the second order term, which on the contrary tend to be negative here, because here we have a square on the blue part. We have a square multiplied by a negative value, which is still always, again, the derivative of the influence function. So this approximation gives us the possibility to identify the values of the biases during interactions with several agents. And we managed to check that this approximate model works well. So here we start with opinions which are regularly distributed between minus 0.6 and 0.6. So these are the columns which are regularly distributed between minus 0.6 and 0.6. So we have the different values, for instance, here. And if you take, for instance, here, this is agent for which the initial opinions, all the opinions are 0.45. So its status is almost the highest. And we see that the opinions about this agent tend to grow. So here with the crosses, this is the self-opinion of the agent, and all the others are the opinion of the other agents about this agent. And the points corresponds to a simulation of 10 million replicas, which are averaged. And the curves, here the solid curve and here the dotted curves, are the model. So we see that we have a good fit. We did it on other values. And to understand better this competition between the positive bias on self-opinion and negative bias on the opinion about others, we introduced this first order equilibrium opinion, which is a combination of the self-opinion and the opinion about self-opinion of I and the opinions about I. So this is a combination of all the opinions about I. And the characteristic of this first order of the equilibrium opinion is that its evolution depends only on the second order value. So the first order terms disappear. So it expresses, and these second order terms actually are the real biases that influence the evolution. So it summarized the tendency of evolution of, on average, the opinions about agent I. And we could show that here the weight on the negative bias is larger when the agent is of low status. So the negative bias hits more the agents of low status. And when there is gossip, the negative bias here is larger when I is low status. So this formula gives us the possibility to explain the difference of competition between the positive bias and negative bias, depending on the status of the agent. And this can be illustrated on the following graphs. Here we are considering, again, with 10 agents. And now we change the inequalities among the agents between them. So this is the range where the different columns are taken regularly from 0.1 to 2. So here we have agents which are very close to each other. So there is a very low inequalities. And when there is 2 here, there are high inequalities. And we plotted the slope of the changes of the equilibrium opinion depending on the status. So and here this is without gossip, and here this is with gossip. So we see that this slope is generally positive, especially without gossip, except for the agent of higher status when there is high inequalities. And we don't see much difference between with gossip and without gossip, except for the agent of status 6, so intermediate status, which becomes to be positive when there are strong inequalities. Now, if we look at agents of low status, so from 1 to 5, when you have 10 agents, so we see that the slope, so the tendency of the opinion about these agents, this opinion about these agents tend to grow almost all the time, except for the agents of lower status, where the opinions about them tend to be to stagnate. The evolution tends to be 0 when there are high inequalities. And we see, contrary to the high status agent, we see a big difference when there is gossip. For the agents of low status, we see that their evolution tend to be negative as soon as the inequalities increase. So here we have negative evolutions of the opinions about the agents of low status. So the agent of low status will have the opinion about them that will decrease very rapidly as soon as there are high inequalities. And this allows us to explain the patterns that I described previously. Because if you start without gossip here, then in the beginning, most of the reputations here tend to grow. And what we have is that the lowest reputation, when you have high inequalities, the lowest reputation tend to stagnate. This is what is predicted by the theory. And here we have bounds on the opinion, so they stop growing when they reach one. And this explains, since the low status stagnate and the high status grow, this explains why we have this average value that grows and then stabilizes. And when we have gossip, remember the agent of low status, as soon as they are beginning to disperse, the agent of low status will decrease, and this is what we see here. And we have much larger inequalities that appear quickly. And you remember we have this agent of status 6. Here we have 40 agents, so we'll have agent of status 18 or 19 that will decrease as well. So here we have a majority, when you have strong inequalities, a majority of agents that have the opinion about them that decrease. Okay, so this is the main result. Now we wanted to know if it's only theory or if we can test these findings from the model on an experiment. So we designed an experiment with 1,500 participants recruited by a specialist firm. And these participants had to answer an online questionnaire. We requested the participant to complete a specific task, and then we gave them a sequence of evaluations about this task and asked them to self-evaluate after this evaluation. So we mimicked the process that I described previously, because the evaluation that we gave them was their self-evaluation plus delta or their self-evaluation minus delta. And we had a sequence of 4 evaluations, 2 positive with plus delta and 2 negative with minus delta. And after each of these evaluations, the participant expressed their self-evaluation, giving us the impact of the evaluation on their self-evaluation. The task was to evaluate the percentage of surface in the picture in green, for instance. And as a result, what we get from each participant, we get a triple with an evaluation, a self-evaluation A, T at time T, the feedback, the evaluation that we give the participant, and the following self-evaluation of the participant. With each feedback, each value evaluation that we give him or her, which is the previous self-evaluation plus or minus delta. And we have that in the hypothesis of our model, the difference between the next evaluation and the previous one is the influence plus or minus the influence multiplied by delta. So we're making a regression of this value, this difference, by the current self-evaluation provides an approximation of the function of influence H. And even we can distinguish between the influence of positive evaluation, positive feedbacks that we call H plus, and negative feedback that we call H minus, because there is no reason that these two functions to be the same as we assumed in the model. So, but I don't go too much in the details. just I go directly to the results. This is the type of result that we get. In here in the axis, you have the self-evaluation. The scale of evaluation was on 100, between 1 and 100. And the y-axis is the difference between the next evaluation and the previous one, or the current evaluation and the next one, divided by delta. And what we observe, and here the lines that you see here, the red line is the regression for positive feedback, so for positive evaluation, and the blue one is for the one for negative evaluation. So, and we see that both lines have a negative coefficient, so they are decreasing, corresponding to our hypothesis, our main hypothesis that function h is decreasing. And as a consequence, we managed to compute bias, as here, a bias that comes from this decrease of the influence function, which is almost 2%. Here it's expressed in a percentage of delta. And this bias is actually higher than the bias coming from self-enhancement, which is the usual bias of social psychologists. And the total bias is the sum of both of them. And this total bias is the difference, the average difference between the value at time 4 and the value at time, self-evaluation time 4 and self-evaluation at time 1. Okay, I conclude. Main results of this work, the moment approximation on the model explains how the biases interact and explains the patterns that we have observed. And the experiment confirms the existence of a bias on self-opinion coming from this decreasing influence. Perspectives. We are working now on an extension of the model to larger populations, introducing other processes, particularly group identity and networks. And also, we are preparing another experiment to check the existence of the negative bias that we have observed in the model. Many thanks for your attention. I'm happy to answer questions now.
Thank you very much for the talk. There are some questions here. One is about inertia. It's a person who takes themselves in high regard, then, as you can read this, then not to change their opinion. On the other hand, not confident people are very negative about themselves, and even doing great things, they think they are not worth. So perhaps in this very interesting model, some sort of inertia, depending on the initial self-opinion, could be introduced. Do you think it could be relevant?
Yeah. This self-inertia is an interesting point. In the experiment, we noticed that sometimes the participants do not change their opinions. I imagine this is what is meant by self-inertia. But what we find on average, of course, these results are of the experiment are really an average on a large number, confirms the tendency of decreasing the influence when you get more, your self-evaluation increases. So I can imagine that if you are in conditions where the inertia is higher, this could decrease this effect, but it should be in very specific conditions where this inertia is increased.
Another question by Eric about gossip propagation. Can you see? Look into society, it seems that bad gossip propagates faster than good gossip and have higher impact of reputation. Does your model allow to discuss this asymmetry?
Yeah, this is an interesting question. here the spirit of this model is to have first something which is as symmetric as possible, to observe where are the sources of asymmetry that comes directly from the, for instance, here in this case, the fact that we have an inference that is decreasing. Of course, if you have asymmetry which is directly injected in model, you will get it in addition to the results. So this is something that goes in addition. Of course, we could, this is one of the perspectives to include other phenomena and to try to observe how these additional biases interact with for instance, the bias that is well known that negative gossip propagate differently from positive gossip.
Okay, thank you very much. Felipe asked to show the slide about the dynamics again, but time is over now. So I don't know if you have already put your presentation in the web page.
No, I haven't, but I will.
Oh,
I will. Yeah,
well, it may be interesting to send the presentation so that
can I send it to you, or can I?
It's to Tiago. To Tiago, there is an email to send.
Okay. Okay. Thank you very much. Thank you.
You can answer, perhaps, I don't know how. So we will pass to the next speaker today, who is Fabiano Ribeiro.
Hello, Celia. I hope that you can see me here.
Yes.
I try to share my screen. Just a minute.
Yes, you are sharing.
Yeah, okay. I hope that you can see my screen.
Yes,
well,
yes,
thank you very much.
Perfect. So you have 25 plus 5 of questions, okay?
Yeah. Okay, thank you very much for the opportunity to be here, and a special thanks to Celia and Duda for the kind invitation. And today I'd like to talk to you about my research, specifically about the scaling laws in urban phenomena, the so-called the physics of cities. And this is my network, collaborative network, that is composed by biologists, urbanists, and physicists, and also my graduate and undergraduate student. I'm from Minas Gerais, Brazil. I'm a professor at the Universidade Federal de Lavras. And what I'll try to talk to you today is about some fractal properties that you can observe in the urban phenomenon, also about the scaling. And also I try to compare these results in cities with biology, specifically with scaling biology. And then at the end of the presentation, I try to present you a gravity idea to try to explain the urban scaling in cities. Fractal is all the object or all the things that have similar properties, no matter the scale that you observe the phenomenon or the object. And in the case of the city, you can use, for example, the box counted method to try to find the fractal dimension of a specific city. For example, if you put small squares to cover the building area of the city, and if you count the number of squares you need to cover all the building area of the city, and if you, for example, if you change the size of this square, of course you decrease the number of squares that you need to cover all the building area. Then, if you plot a graph, for example, the number of square as a function of the size of the square. And if you have a straight line in the log-log plot, has this one here for the city of Newark. And if you have this straight line, that means that you have a fractal object. So specifically, the slope of this straight line represents the fractal dimension of the building area, here specifically in the case of Newark. In fact, this straight line is the signature of a fractal behavior. And for example, here you have many cities in China that also have this straight line in this log-log plot. That means that this city, in some sense, is a fractal object. And there's other kinds of of fractal dimension when you consider the city. For example, you can measure the total length of the length of the street of the city, and also have a fractal dimension associated with the total length of the city. And also, for example, there's other kinds of fractal dimension related with the spatial distribution of the population in the three-dimensional space that embedded the city. And what have a special empirical result here is that beside the fractal dimension related with the total length of the street and the fractal dimension related with the spatial distribution of the population are different numbers, as is shown here by this empirical evidence. Here, every point here represents one city with a population n. So these two quantities is different, but the fraction, the ratio between these two fractal dimension converge to a number, give it a sufficient large city. And this number will be special, will be very interesting for us when we were talking about the scale, urban scale, in fact. And not only objects can be called fractal. In fact, any variable that have independence of the scale could be called a fractal. And the way that we can see if a variable is a fractal or not is to try to see if the log-log plot between this variable in the some metric have a parallel behavior, for example. That is one way to see if you have a fractal properties. And here you have a GDP that is not a spatial kind of thing, but is a variable associated with health of the city. And here every point represents one particular city in USA and Brazil. And you can see that you have once again the signature of a fractal behavior. That is this straight line in this log-log plot. That means that this equation here, this parallel equation, represents very well this set of data. And one thing that called the attention, especially the physicists the last years, is that the slope of this straight line is around 1.50. And that is some kind of universal number, because many countries around the world present this same number. The fact that this number is larger than 1 means that you have an increased return to scale. That means that when you have, that means that larger cities also have a larger GDP per capita. That means that larger cities are richer than the small ones. And for example, here you can see the strongness or the robustness of this scaling property, because here you can see that the chaotic movement of the individual cities through the time. However, the slope of this red straight line is approximately the same. That means that beside the chaotic movement of an individual city, the scaling property is stronger and preserved through the time. And usually the explanation for these scaling properties comes from have a fundamental explanation that is related with the number of contacts of the people that increase with the size of the city. For example, in this Bittencourt paper, he and his colleagues shows that the mobile phones contact also increase with the size of the city. And the exponent of this scaling property is around 1.12. That is very similar to the exponent that we have observed in the case of GDP. However, there's other kinds of variables usually associated with infrastructure that present a sublinear behavior. That means that the beta that's related to the number of these infrastructure variable, in this case here specifically is the number of petrol stations. This number is scaled with the population of the city according with a scale exponent that is around 0.85. The fact that this number is smaller than 1 means that you have you have a scale economy. That means that when you increase the size of the city, you decrease the infrastructure per capita. And that means that bigger cities have less demand for infrastructure, or that's a scaling economy in some sense. And Bittencourt classified these variables in 3 groups. In fact, there's a group of variables that have beta smaller than 1, and usually these variables is associated with infrastructure. And of course, there's some exception for this rule, but most of the variables that is associated with infrastructure have these properties, that beta is smaller than 1. That means that you have a scale economy. And there's a second groups of variables that is usually associated with individual needs that have beta is equal to 1. That means a linear behavior between these variables and the population size of the city. And then the third group is associated with some kind of socioeconomic variables. And these kind of variables have beta greater than 1. That means that you have increased return to scale. That means that you increase the size of the city, you increase the per capita socioeconomic quantity. When I compare this result with other very low scaling properties, that's the case here in the biology, and of course we think that maybe we can do some analogy between this evidence that we have observed in the case of the city with the biology. And for example, here we have also a scaling or a power law that describes the metabolic rate of some biological organism as a function of the mass of these organisms. And if I consider vascular systems, that means that organisms that have a circulatory system, you have a well-known 3-quarter exponent that describe this equation, that the exponent of this power law equation. But this works only for vascular organisms. For other kinds of organisms, as is the case here, the beta could be different, could be superlinear, for example, could be linear. But in this case here, in the right side of this graph, this 3-quarter law apparently works well. And the fact that this 3-quarter property in the case of the biology means that you have a sublinear behavior in the same sense that you have a sublinear behavior in the kind of infrastructure in the urban system. That means that both in biology or in urban phenomena, you have a scaling economy. In the case of biology, when you increase the size of the organism, you decrease the energy demand per cell. And in the case of city, when you increase the population of the city, you decrease the infrastructure per capita. That means the scale economy in both biology and cities. In the case in biology, we have a theory to try to explain this 3-quarter law, 3-quarter property. For example, this theory here that was proposed in the late 90s, that considers that the fractal network distribution and terminal unity, for example, cells and capillaries, do not vary with the size of the organism, together with the natural oscillation, the minimization of energy. When you consider these 3 arguments, these 3 assumptions, you come up with this exponent 3-quarter. And fractal network distribution means that you have a hierarchical property to distribute the nutrients to this from, for example, the aorta to the capillaries and then to the cells. And when I look at this figure here, and you have on the right the circulatory system of the human body, you can see this hierarchical property of this circulatory system. And also when I see this figure that represents the metro lines in Berlin, you also see some kind of hierarchical property, and also have this fractal behavior of this transport system. And also this image that represents the streets of Shanghai also show us that you have some kind of hierarchical properties in this system. But this is only a qualitative analogy, because when I see the quantitative analysis, cities and biology are a little bit different. Both of them are well described by power law. However, the exponent is different. And the fact the exponent is different leads to different in the terms of a scale economy. In the case of city, you have, when you increase the size of the city, you have a scale economy of 50%. However, in the case of biology, when you increase the size of organism, you have a scale economy as well. However, with a 25% of a scale economy. That means that biology is more efficient than city in terms of quantitative terms. Here we have some models that I and my colleague Diego Hibes are organized to, and here we have the models that try to explain the scaling properties in the case of urban phenomena. And you can see that you have a lot of models in the literature. You have models that consider intra-urban process. You have models that consider inter-urban process to try to explain urban scaling with no consensus at all. That means that this subject is still lack of general theory. You have only theories that explain very particular, some case of urban phenomenon. And what I try to concentrate in the last part of my presentation is about a model that I and my colleagues propose that is based on gravity models, based on some physical ideas of gravity models. And the model to try to explain the urban scale is to think that you have two pairs of individuals that are at distance r from one from each other, and the probability of interaction between these two persons decay with the distance according with this formula. Okay, and this formula have a parameter here that I call gamma, and gamma measures the range of interaction between these two guys. And for example, this formula is strongly supported by some empirical evidence. For example, the distribution of Facebook contacts and the distribution of email according with the distance is well described by this equation. And also a recent work that was published in Nature also support this parallel behavior between the number of times that the people visit a place that is distance r from the origin, also have this parallel with exponent 2 here in this case here. This empirical evidence, thousands of people carry a mobile phone, and then by GPS you can identify the position of this person, and you have here a strongly universal, apparently universal behavior in different cities, in different cities around the world. And the model that I'm considering is try to use this idea, this gravity idea, to model the interaction between the people. And then I consider also that the people are distributed through the space, has a fractal structure, okay? And then with this idea, I can compute the number of contacts of the people. And I consider that the socioeconomic output of the city is proportional to this number of contacts. So what I need to do is to compute how many interactions I have in the city. And I use this equation here, when P is the probability of interaction between two persons, who describe the spatial distribution that is a fractal structure that the people are in the city. When I solve this equation, what emerged from this calculus is that scaling properties only emerge when you have some kind of long-range kind of interaction. So when the city interacts as a whole, then you have a scaling property, as we observed in the case of empirical evidence. However, when you interact only with the people that is in your neighborhood, you have a linear behavior between socioeconomic and population size. That is not what we have observed in the case of the empirical evidence. That suggests that maybe we interact with our friends, with our colleagues, or with our neighbors, or with any person in the city has a long range kind of interaction. And also the model also suggests that we can write the beta parameter, the scaling exponent, has a function of the geometric parameters of the model. Here we have the beta has a function of the range of interaction between the people described by this gamma parameter, and the spatial distribution of the people in the city by this fractal dimension, dp, that is a fractal dimension of the structure formed by the people through the city. And using the same idea, I can compute or can predict the number of amenities, or number of petrol stations, number of bakeries that you can observe in the case of the city. And if I consider that R now represent the distance between the one individual, I, and a amenity, or a baker, or a petrol station, K, and if I model that the F has, for example, the number of products this guy buy in this specifically amenity, and I model that is also a power law that you have the K parameter gamma, the same gamma that I use in the previous slide. And then when I use this model here, I can, for example, compute the number of products that this guy buy in all the amenity through the city. If I sum this quantity with all the individuals of the city, we have the total amount of this product that was bought in the city, or that was consumed in the city. And also, if I consider that this product that I'm talking about is about an individual need product, that means that this product is scaled linearly with the population size. When I put this information here in this model, what emerged is that once again, beta that now is not a is a sublinear kind of a parameter. That beta also can be right in terms of the geometric properties of the city. Well, and there's only to compare the result with other models in the literature. We have here some kind of phenomenological kind of model to try to explain this scaling property, this scaling parameter. For example, we have here, how I told you in the beginning of this presentation, we have two fractal dimensions, one associated with the length of the city, and one fractal dimension associated with the spatial distribution of the population. And when I put together these two formulas here, we can say that the total length is scaled with the n, the population size, erased to this ratio, the ratio between these two fractal dimensions. And if I consider that the amenities, the bakeries, or the petrol station are attached to the streets, that means that the total amount of these amenities is proportional to the total length of the city. That means that the total number of these amenities is scaled with n erased to this ratio again. And how I told you in the beginning, the ratio between these two fractal dimensions is around 0.86. That is exactly the same number that you have in the case of the scaling of infrastructure in the case of the city. And in fact, when you plot the total length of the streets as a function of this quantity here, m erased to this ratio, you have a straight line with exponent 1. That means that L, in fact, scale with n erased to this ratio. Okay, when I compare these two models, for example, the Molineros and Tanner model, that is some kind of phenomenological model, with your model, this is a kind of microscopic model. What suggests with the comparison between these two models, and also through these two models have equivalence between themselves, we need that the probability of interaction between the people must scale by this formula. And this part here of this equation, in fact, is the length of the city, or how the length scale with the size. And that result suggests that the way or the form or the shape of the streets affects the probability of interaction between the people, and consequently, this probability of interaction interfere or govern the scale that we have observed in the case of the city. Well, thank you very much for the opportunity. And if you have more interest about this research that I have presented to you, I suggest that you take a look on this paper that I have presented, some new result of my team and my research, and the model that I have presented here, you can find in this paper that was published in the Royal Society of Science. And thank you very much. And if you are interested in other works that I have, I suggest you take a look at my webpage that you can go by this QR code and see all the information about me and my research and my collaborators as well. Thank you very much, and open to the question.
Thank you very much, Fabiano. There are some questions we want to read here. There is a comment or question by Steve Lawford that comments about Xavier Gabe have done so. Can you see? Fabiano has.
Yes, I can see here the questions. I don't know where to begin the question for me.
Do you want to comment something about this comment?
If you want, I can read here the comment.
Yes,
Let's try, for example, Xavier Gabex has also done some work on scaling cities and discusses suitable underlying economic mechanism. I think that is on the suggestion here. Okay, thank you very much, Steve, and take a look at this Xavier paper, Xavier work.
Albert.
And Albert, very nice idea, comparing infrastructure of a city to the metabolic distribution of nutrients in organisms. But there's an important difference. Cities may display huge heterogeneity of infrastructure, depend if you live in rich or poor neighborhoods. In that case, does it make sense to talk about a scale exponent of the city, a single scale exponent of the city? Yes, the answer for this question, Albert, thank you very much for this answer. I think that's a very important answer. And in fact, the analogy between biology and the city is only qualitatively. Quantitatively, I have showed to you that is completely different. And of course, I think universality in urban phenomena is a concept that is difficult to accept. Of course, cities is very complex, and any variables subject to this our own. Every variables in the city is different from each other. That's the problem. And I'm very, how can I say, previously I was an enthusiast about the universality in urban phenomena, but now, passing some years studied that, I'm upset about this to call universalities in the case of urban phenomena, because I agree with you that is very complicated matter and a very complex system, and it's difficult to accept the universality in this case. Thank you very much. And
Felipe.
Other question, Felipe, do you think this kind of analysis could be used to analyze abstract infrastructure, like the size of the judicial system of the state? I don't know, but for example, GDP is also abstract. But okay, GDP is a socioeconomic output. But I don't know. We need to take a look at the data and see what the data tell us about. And Marcus, maybe you will find interested in this article, and Mark suggests other articles. Yeah, I think that is what we have here in the chat.
Okay, there are no more questions. We are over the time, so I will pass to the next speaker, but I stimulate people to go on asking questions on the chat and the speakers to keep reading to answer. So perhaps, thank you very much, Fabiano. The next speaker is Ariel Salgado. Can you share the screen?
Can you see my screen now?
Yes.
And hear me?
It's okay.
Yes. Excellent. Well.
So Ariel Salgado is from Buenos Aires, Ciencias Exactas y Naturales de Universidad de Buenos Aires. He's going to talk us about collaborative networks of software.
Well, hello everybody. My name is Ariel Salgado. I'm working with Inés Caridi at the Calculus Institute at the University of Buenos Aires. And first of all, I want to thank the organizers for the opportunity to tell you part of my PhD work. And during this talk, I will present a complex network analysis on CRAN, the R network of packages. So I want to give you some reference on how to locate this work in relation to some general complex networks topics. This analysis falls under two topics. One is collaborative networks, like the paper citation network and the co-authorship network studied by Newman. And the other is software networks, which includes networks of functions and methods, like, for example, the functions of the Linux operating system. Under both, we have the package dependency and package recommendation networks. And in the former, software packages play the role of nodes, and their relationships represent a package requirements in terms of other packages, while in the latter, packages are connected if one suggests another to be installed. So, from all the languages and package libraries, why CRAN and R are interesting? R is an example of a growing system which passed from just a few packages in the 2000s to more than 12,000 packages in 2020. CRAN is the official library where R packages are stored. From CRAN, we consider three types of elements: packages and dependencies and suggestions, which are relationships among them. Packages seem to increase exponentially in time, and the amount of relationships grow faster than the number of packages, surpassing them nowadays, as you can see in this plot. The growth of CRAN accompanies the growth of a worldwide community of R users. In this sense, the evolution of CRAN can be seen as part of a bigger process related to a community of developers and users in constant evolution. Studying CRAN gives us insights of the evolution of the R community, but also provides a detailed example of a growing collaborative network. With this in mind, let's see what we find when we have a look at CRAN. In short, a package consists of an extension of the basic functionalities of the language. It can take advantage of other existing packages, connecting to them through relationships. As I previously stated, there are two types of relationships: dependencies and suggestions. Dependencies, shown in the left for the package caret, are similar to citations, where a package has directed connections pointing to the packages using it. In this example, the dependency tree of caret shows us that it uses ggplot2, model metrics, and others, while also many of these packages relies on others too. On the other hand, the suggestion network, shown in the right, is based on the tutorials included in each package. Two packages are connected through an undirected suggestion link if they are used together in a tutorial. Both networks provide us with a sense of collaboration. Dependencies represent the creation of new ideas based on previous packages, while suggestions represent possible combinations among them. So, following these two relations, we constructed two growing networks, one per relationship. We used them to study CRAN's evolution. We separate our results into two types. One is the macroscopic growth of the network, described by the biggest connected component, or BCC, and the mean degree. And the other is the microscopic growth, where we consider the degree distribution and its sources, the number of connections included by new packages, and the preferential attachment to previously published packages. In the end, I will also add a commentary on how this relates to external events in the R community. So, considering the macroscopic growth, the mean degree represents the number of connections an average package has. It shows us how the connectivity of each network increases. In the dependency network, it can be seen as multiple linear regimes with slightly different slopes. In the suggestion network, there are at least 3 different stages with clearly different slopes. The mean degree indicates breakpoints in each network where the number of connections added per package changes. The other measure we consider is the BCC. It can be seen in opposition to the fraction of independent packages, disconnected from the rest. At any time, as shown in the plot on the right, the sum of both represents at least 80% of the network. So both networks can be seen as one cluster and multiple independent packages. As shown from up to down here, as the networks evolve, they transition to mostly BCC from mostly independent packages. So, having a look at the degree distribution, we split the dependency degree into 2 types. The dependency in degree, which represents how many packages another needs to work, and the dependency out degree, which represents the number of dependent packages another has. For the suggestion degree, we just considered the undirected degree. Both the dependency out degree and the suggestion degree have power law distributions with exponents near 2 and have very little changes during the evolution. On the other hand, the dependency in degree resembles a log normal distribution. This way, these distributions shows us that the in degree is bounded as packages with high in degree are non-existent. On the contrary, packages with a high number of dependencies and suggestions are not uncommon. To better understand how these distributions arise, we measure how the dependency and suggestions included by an incoming package changes through evolution. We found an interesting relation. The average number of connections at arrival increases with the size of the BCC, as shown in the left panel in the upper section. Even more, the distribution has a stationary shape once normalized by that mean degree, as shown in the right panel. Thus, we found that we can represent it like a zero-inflated log normal distribution with 2 parameters, depending on the fraction of packages in the BCC, but otherwise fixed. We conclude from this that as the number of robust options to connect with increases, there is a fixed behavior represented in the steady distributions of dependencies and suggestions at arrival. On the other side of the network's growth, we have the preferential attachment. It represents the tendency of a package to connect to the most connected packages. Using a methodology proposed by Young et al., we measure the degrees of the selected packages at different times. We consider the dependency out degree and the suggestion degree as measures of importance. The obtained distributions are consistent with preferential attachment function with a power law shape for the dependencies, as shown here in the left. But for the suggestion, this only holds for low degrees, as you can see here, but then there is a change in the code. We can say that both networks have superlinear preferential attachment, but for the suggestion degree, there is a more complex shape. Conceptually, highly connected packages are preferred to the rest, especially in the case of suggestions. Finally, I want to comment that many of the changes in the connectivity can be correlated with changes in the programming language guidelines and the publications of specific packages. For example, changes in the versions of R produce changes in the trans connectivity as represented by the mean degree or the BCC. Or the changes in the suggestion preferential attachment can be linked to the publication of specific packages, aiding to the development process of new packages. This is relevant as it shows us that understanding the structure of the network allows understanding the effect of these external events. So, in conclusion, CRAN poses an excellent example of an evolving collaborative network whose external events can be related to the changes in its growth patterns and connectivity. Preferential attachment is found in dependency and suggestion networks. Both of them have superlinear preferential attachment, showing a high preference for connecting to the network's hubs. The number of added connections per package increases as the BCC grows. However, the distribution shape remains steady through evolution. We can relate this to an increase in the number of reliable options represented by the BCC, which only changes the scale of the number of selected packages at any time. And finally, both networks can be seen as one giant cluster and a myriad of independent packages. As the network grows, the fraction of independent packages reduces and the giant cluster represents the biggest part of the network. I want to also mention that the associated database represented by CRAN is extremely rich, allowing to study other aspects like connection removal, intersection of networks, and others. I left out these results due to the time restrictions of a talk. So that's all. Thanks a lot for your time, and I'm reading the questions if there are any.
Thank you very much, Ariel. There is at least one question. Do you want to read?
Let me see.
Albert
Niels, do you know about this type of network description for other languages? How they compare to? My impression is that if you have power laws for a language, it means that it might not be very versatile in its architecture. Too many dependencies. Well, retaining the second part of the question, referring to Albert's impression, I believe that that's true, but studying it deeper, which I couldn't include in this work, you can see that this excessive number of dependencies corresponds to the trees. Let me see if I can go here. It is typical, this type of structures that you can see here, where caret depends on model metrics and also on plier and also on RCPP. And there is the formation of something similar to the clustering coefficient in other networks, which here is more like something like a fan of connections from older packages to newer packages. So this type of power law distribution doesn't correspond to an excessive, truly excessive number of connections, but to some superfluous connections connecting a package with its direct ancestor and with the ancestors of the first layer of packages to which it connected in the first time. On the contrary, in the suggestion network, these are not dependencies, are tutorials. So having a lot of connections here, it's something that is good because it represents that there are packages which are really versatile and used in a lot of tutorials. And at last, the comparison with other languages. I personally didn't explore other languages, but what I can say is that this model, which I was, this situation which I was telling you about regarding the fan structure, was already studied in some models regarding software networks. So yes, there is some common situation in other networks too. Okay, thank you. Are you referring to the software systems of the network of the Linux community, or yes? Okay, thank you. I will have a look at that.
Okay, thank you very much. Another question, not in the chat, but if you want to raise hands, I don't see here. We are almost in the time anyway. So thank you very much, Ariel, and
thank you very much.
We can pass to the next speaker.
Yes, so hello everybody. So let me just share the presentation.
Hi, Arkadiusz. Yes.
Hi, thank you for having me here. So yes, it should be now visible. Yes, all right.
Yes, it's okay.
Yeah, so maybe I can start. So hello everybody once again, and today I would like to talk about a simple agent-based model with local and global interactions. So let me start with the motivation behind this study and also an explanation what exactly we mean by local and global interactions. So in our study, we distinguished between two sources of social influence. The first one we call a local source of influence, and these are interactions between people that already know each other. So these may be interactions between friends, family members, or just neighbors. However, nowadays we can be also easily impacted by people that we don't know, strangers. And this is because common access to mass media or different networking websites. So these interactions between strangers, we would call global interactions. And what is interesting is the fact that there are some studies that indicate that these different types of sources of social influence may cause different human behaviors. And for example, in this particular study on movie ratings, the authors found out that people always tend to conform to their friends' ratings, whereas ratings issued by strangers may cause either conforming or anti-conforming behavior, depending on the movie popularity. So this observation that different types of social influence like conformity or anti-conformity may be related or somehow correlated with different interaction lengths prompt us to study a model of opinion dynamics that already includes these two types of social influence. However, this time we want to study this model with this distinction between different ranges of interactions. So what model we consider? This is a Q-voter model. So to give you a big picture how this model works, let me say that this is an agent-based model. So we have voters on the network. This network represents a social structure. In this case, this is a friendship network. And the source of social influence in this system is the group of Q randomly picked agents or voters from the system. And this group of influence may cause either conforming or anti-conforming behavior. And this is also a binary state model. That means that each voter in the system has a positive or negative opinion represented by a variable that can be in two states. And such a dichotomous format of opinions is also commonly used in empirical psychological studies. So how exactly this model works? So this model has two parameters. The first one is the probability of anticonformity, and the second one is the size of the influence group. So in the system, we have many voters, and then one after another, we choose a voter randomly, and then with probability P, this voter at a given time step can act as an anticonformist, and with complementary probability, it acts as a conformist. And in both cases, we have to collect this group of influence. And this group of influence is constructed based on choosing randomly Q voters. And when this group of influence is unanimous in opinion, then in the case of anti-conformity, we take the opposite opinion to the group opinion, whereas in the case of conformity, we take the same opinion as the group has. And there is also this third case when we don't have agreement in the group, the influence group, but then our voter doesn't change its opinion. So this is how the model works. And in its original formulation, all the interactions were local, in the sense that the members of this influence group were chosen from a direct neighborhood of a given voter. So this neighborhood was defined by the network topology. And in our study, we wanted also to include this notion of global interactions. And our idea to include these interactions was quite simple. So in the case of global interactions, we allowed voters, the members of the influence group, to be chosen randomly from all the voters in the system without regard of the nearest neighbor structure. So since we have local and global interactions and also two types of social influence, we can construct, in fact, 4 different Q-voter models with different combinations of these local and global interactions. And we want to compare them. So I would like to highlight at this point that the model with both global interactions corresponds to a purely mean field model, in the sense that the network structure doesn't matter for this model. And this model will serve us as a benchmark to compare other models. Whereas the model with global anti-conformity and local conformity is the model that the best corresponds to the situation we had in this empirical study on movie ratings. So what do we study? We study public opinion, which is just an average opinion in the system, or equivalently, the concentration of positive agents. And what we want to find out is how the network structures impact the phase diagrams of our models, and how different models and what are the phase diagrams for different types of interaction. So in our study, we distinguish between 2 phases. The disordered phase corresponds to the situation in which both opinions are equally likely in the system, whereas the ordered phase is the phase in which one opinion dominates over the other. So to find out what are the differences between models, we took both analytical and numerical approach. And the analytical approach is based on pair approximation. So the pair approximation is just an enhanced version of a mean field approximation, in which we also take into account dynamical correlation between nearest neighbors. And this is done by taking into account also concentration of active bonds in the system. And what is nice in this pair approximation is the fact that based on this approach, we can derive analytically the phase diagrams of our models and also derive exact formulas for the transition points in these models. So what we get from the pair approximation is that the only property of the network that should influence the phase diagrams is the average node degree. However, of course, this is the result only based on the pair approximation. So we suspect that in simulation we also see other properties of the network that will also impact the model. But about the simulation, I will tell on the next slide. What is important here, we get that on the slide, we see how the phase diagrams changes when we increase the average node degree of the network. And we see that the limiting behavior of all these models is the same. So when this average node degree tends to infinity, all the phase diagrams for different models tends to the phase diagrams obtained for the mean field model. So this begs the question whether this distinction between different interaction lengths is relevant in real systems, since maybe in real networks, this average node degree is high enough just to neglect the differences between different models. So to answer this question, we just set this average node degree of the network to be the same as in this correlation study on movie ratings. And in this correlation study on movie ratings, this average node degree was 50. However, now we have to somehow choose the size of the influence group size. And here we have some hints from social psychology that the groups that are the most persuasive are those that are comprised of around 3 to 5 people. And when we set our model to these parameters, we see that we still see some differences between different models with different interactions lengths. So so it seems that this distinction between different interaction lengths is justified and relevant for the dynamics in real systems. And as I said, these were only analytical results, but we suspected that there are also other properties of the network that are relevant for the phase diagrams. And that's why we simulated our model on different networks. And here I present the results for what's Strogatz networks. And these networks have a nice property, that is that there is a parameter beta that corresponds to rewiring probability in these networks. And when we change this rewiring probability, we change different properties of the networks, like the average clustering coefficient or the average path length. However, we do not change the average node degree. And this is yes, okay. Okay, so this is nice because in this per approximation, we get that our solution should only depend on the average node degree. So if this were the case, we would not have any dependencies on these parameters in the simulations. And this is the case only with the model with local anticonformity and global conformity. So this model seems to be, in fact, insensitive to changes in the network structure as the per approximation predicts. However, models with local conformity, they do depend on the network structure. And it turns out that the model with global anticonformity and local conformity is the most sensitive to these changes. So just to conclude, I would like to say that studying models of opinion dynamics with this distinction between local and global interactions may bring us interesting results. And in particular, in this Q-Voter model, we found out that this mixture of global anticonformity and local conformity resulted in the model that was the most sensitive to the network structure. And interestingly, when we change the ranges of interaction in this model so that we get the model with local anticonformity and global conformity, the network structure is completely irrelevant, for the dynamics of the model, and only average node degree matters as the per approximation predicts. So thank you for your attention. If you have any comments, you're welcome.
Thank you very much, Arkadiusz. There are some questions,
Okay.
Although we have less than 1 minute. But
okay, so maybe I will read them and yeah.
Yes, please.
the first one is, can you determine this
yes.
one? Determine in advance that a certain network is going to go through a phase transition. Should this be useful to predict results? Yeah, so not exactly, since we have to simulate or we have to conduct the analytical calculations. So in fact, we get phase transitions. I mean, in the simulation, we of course have to conduct the phase, the simulation in order to state which type of phase transition we have to we will get. However, the pair approximation do not correspond to the results from the Monte Carlo simulation in all the cases. So so yeah, so this is. It's hard to state, yes. And whether we use that to predict elections, is this useful? It's also hard to, we don't think about this model as a model to predict something. We rather are focused on studying microscopic properties of this model and found out what these microscopic properties will give us on a macroscopic level. So this is the basic ideas behind our studies. And I see that there are more questions, so maybe I will answer them on the chat because how much time I have. Did you consider the presence of special agents in your model? Like, no, so no, this is thing what we can do later on, because we only consider this anti-conformist and conformist. But yes, this would be also interesting to study other agents. And the last one. Okay. So I have basically answered all of these. Thank you.
Okay, thank you very much. Now we will have a break, but I want to make an announcement before, so about a special issue before the break. Perhaps you can stop sharing.
Yeah, sure.
We have no image. I want to tell you that we, the organizers, have done a proposal for a special issue on sociophysics to chaos, soliton, and fractals, and this proposal has been accepted. We have still to define some details, but we want you to know that this possibility exists, so you will receive soon information. So pay attention, just to tell you to pay attention to the details that maybe we want to communicate as soon as the details are defined, okay? But there will exist a special volume, special issue on, not linked to the event, but on sociophysics in causaliton and fractals. That is all, and we have now a break of 15 minutes. 12, actually.